You guys can able to see my screen, right? Okay, so welcome to iitian classes. So today we will be discussing on jet propulsion part of Gate Aerospace 2012 paper. So myself Akshay. Then in 2012, relatively there are very less number of questions asked from jet propulsion part. There were around 8 marks question, 8 marks being asked from core jet propulsion, with 3 being 2 mark question and 2 being 1 mark question. So one point I want to highlight here is like out of these 8 marks, so 5 marks for grace because they are given marks to all due to lack of data or incorrect options given in the question. So let us try to see the questions from 2012 paper. The first question is fairly straightforward. The ratio of flight speed to exhaust velocity for maximum propulsion efficiency is. So, which of this is correct? It has to be option C, right? Because we know for again they are not given the type of the engine. Let us assume it is turbojet engine. So for that we can define a propulsion efficiency to be 2 alpha divided by 1 plus alpha, where alpha is ratio of forward speed to jet exhaust velocity, CJ. So that's what they're asking. What is a value of alpha for a maximum propulsion? Maximum propulsive efficiency is like we can achieve is 100%. If I want to achieve 100% efficiency, that becomes eta p is 1. So 1 plus alpha is equal to 2 alpha, or alpha is equal to 1. So Ci by Cj should be 1. Option C. Okay, so straightforward. This question is like a really a good question with lack of data. So like not data, the statement should have been much more clearer. The ideal static pressure coefficient of a diffuser with an exit with an area ratio 2.0 is. So very good question. Only thing they should have added is like incompressible ideal diffuser. So that makes this problem much more clearer. So say like let us assume this one. So I will mark it as a star because it was given as a grace. Okay, but let us try to solve this problem by assuming it is an incompressible diffuser. So what do we mean by a static pressure coefficient? So we define this particular non-dimensional variable called a static pressure coefficient, Cp, as P minus P infinity divided by half rho infinity V infinity square. So by the free stream dynamic pressure. So this is how we define the static pressure coefficient. So now what is given in the question? They are given the ratio, area ratio. That is area at the exit to area at the inlet is given as 2.0. So this is given in the problem. So being keeping this in mind, so we have to calculate what is Cp. So if I assume it to be an incompressible condition, then what I can do is I can use a streamline, any streamline, which connects point 1 to point 2, and apply a Bernoulli's equation along the streamline. So I can actually get back to the answer. So see, let us say this is point 1, this is point 2 at the exit, right? So here I have a free stream condition, V infinity. Here I have some velocity which is exiting from the diffuser, so and entering to the compressor. So say call it as V1. Okay. So now if I apply the Bernoulli's equation, so that is a limit for energy equation in incompressible flow field, that turns out to be a momentum equation. P naught is equal to P plus half rho V square. It is constant, right? That is the Bernoulli's equation for incompressible rotational flow field and steady flow field. Okay. So P plus half rho V square is constant. So now if I apply over here, this is P infinity plus half rho infinity V infinity square, that is also should be equal to P1 plus half rho 1 V1 square. So I can write like this. Okay, let us keep this part one side. So all I have to calculate from here is like what is P minus P infinity, P1 minus P infinity. Okay, from here. So if I assume it to be an incompressible flow field, so then I can also relate a volume flow rate. That is Q is constant, right? So that is nothing but A1 V1 should be equal to A infinity V infinity. So I can write A1 by A infinity. That is nothing but from the given information AE by AI, which is equal to 2.0, which is equal to V infinity divided by V1, right? So now look back our Bernoulli's equation, that says me P1 minus P infinity is equal to half rho is constant, so I can take outside, equal to this V infinity square minus V1 square. If I take V infinity square outside, that becomes half rho infinity V infinity square times 1 minus V1 by V infinity square, right? So now what is V1 by V infinity? That is 1 by 2. So half rho infinity V infinity square times 1 minus 1 by 2 whole square, that is 1 by 4. So if I take the LCM, it becomes 3 by 4. So that is nothing but 3 by 4 times half rho infinity V infinity square. So that is P1 minus P infinity. So now use the definition of Cp. That is P minus P infinity divided by half rho infinity V infinity square. So P minus P infinity we calculated here. That is 3 by 4 of half rho infinity V infinity square divided by 1 by 2 rho infinity V infinity square. So I can cancel out these two. So that becomes 3 by 4. What is 3 by 4? That is 0.75, right? So option C would be correct. So everybody clear? Yes. It was like a really good question with one information that is missing. If they had mentioned it's incompressible diffuser, you could have proceeded. Okay. So let's go to the next question. The stagnation temperatures at the inlet and exit of a combustion chamber are 600 Kelvin and 1200 Kelvin respectively. If the heating value of the fuel is 44 megajoules per kg and the specific heated constant pressure for air and hot gases are 1005 joules per kg Kelvin and 1147 joules per kg Kelvin respectively, the fuel to air ratio is. Again, very straightforward question. So first we will try to draw control volume enclosing the combustion chamber. Okay. So what else we have here? We have incoming condition. outgoing condition, that is T02 is given as 600 Kelvin, T03 is given as 1200 Kelvin. Here the mass of air is coming in, here the mass of gas is going out, that is equal to mass of air plus mass of mass flow rate of fuel. So that means mass flow rate of fuel is added to the system, which has a calorific value QCV as 44 megajoules per kg. This is what given. So Cp for incoming air is given 1005 joules per kg Kelvin. Cp for the gas which is going out of the control volume, that is given as 1147 joules per kg Kelvin. Okay, so this is what given in the problem. So they are asking you to calculate fuel to air ratio. So again, it's a classic problem. So we will try to do this by doing energy balance, that is H03 is equal to H02 plus energy addition, which rises the total enthalpy of the system. So that is nothing but mass of the fuel added times the combustion efficiency times calorific value of the fuel. So if I use this idea, so here I can write mass flow rate of gas times Cp of gas times T03 equal to mass flow rate of air times Cp of air times T02 plus mass flow rate of fuel times combustion efficiency times QCV. So mass flow rate of gas I can split as mass flow rate of air plus mass flow rate of fuel. Cp of gas times T03 equal to mass flow rate of air times Cp of air times T02 plus mass flow rate of fuel times Cp. So now if I take mass flow rate of air common, so I can define fuel to air ratio to be mass flow rate of fuel by mass flow rate of air. So if I take mass flow rate of air common, that gives me 1 plus mass flow rate of fuel by mass flow rate of air, that is fuel to air ratio times. Here also if I take mass flow rate of air common, that gives Cpa times T02 plus mass flow rate of fuel by mass flow rate of air, that is F times eta B times QCV. I can cancel out mass flow rate of air from both the side and taking all the terms with F. So I can write it for fuel to air ratio as Cpg T03 minus Cpa T02 divided by eta B QCV minus Cpg T03. So now everything is known to us. Cpg is 1147, T03 is 1200, this is 1005, 600, and eta B is 100% because since it's not given in the problem, so we can assume it to be 100% efficient combustion. So we can put the values over here. 1147 times 1200 minus 1005 into 600 divided by, this is 44 into 10 to the power of 6 minus again 1147 times 1200. So this should give you F as 0.018. So I think it's a MCQ. Yes. So 0.018, that is option B. Clear, right? Yes. So let us move to the next question. Again, this question I will mark it as star because it is again given as a grace. Okay, but let us try to solve this problem anyhow. So its mark is given to everybody, but we can actually still go on to calculate this problem. Okay, so air at a stagnation temperature of 15 degrees Celsius and stagnation pressure 100 kilopascal enters an axial compressor with an absolute velocity of 120 meter per second. Inlet guide vanes directs this absolute velocity to the rotor inlet at an angle of 18 degree to the axial direction. The rotor turning angle is 27 degree and the mean blade speed is 200 meter per second. The axial velocity is assumed constant through the stage. The first part they are asking the blade angle at the inlet of the rotor is. In the second part they are asking if the mass flow rate is 1 kg per second, the power required to drive the compressor is. Okay. So now, so let us try to draw the given information systematically. I have a rotor which is rotating in this direction, and before that, like the flow entering the stage with the help of inlet guide vane, it is directing the flow with an absolute velocity c1, and it is already rotating at u. Let me just redraw it. C1 W1 with respect to axial velocity, that's an angle alpha 1. This has angle beta 1. That means the inlet guide vane is guiding the flow in this direction. Okay, and it exits the rotor at an angle C2 W2 beta 2 alpha 2. Okay, so now the velocity triangle is clear. So what they are given, they are given that this velocity vector is having an angle with respect to axial velocity vector, that is alpha 1, as 18 degrees, right? And they're also given that as the flow passes through a rotor, it turned by 27 degrees. That means they're given that beta 1 minus beta 2 is 27 degree, which is the turn angle. Okay. And other information they are given is the blade speed at the mean blade radius, that is 200 meter per second, and they are given the other condition at the inlet, that is if I take a control volume enclosing a compressor stage, so that is the flow which is entering with the stagnation condition of 15 degrees Celsius, that is 288 Kelvin, and pressure P01, that is 101 kilopascal, right? And absolute velocity vector, the value of absolute velocity vector is also given, which is entering with a velocity of 120 meter per second. So now if I have C1 and I know what is alpha 1, I can calculate CA, right? From this triangle, if I use the cosine of alpha 1, cos alpha 1, that is going to be CA divided by C1. So I can easily calculate what is CA. CA is C1 times cos alpha 1. So if I calculate that one, axial velocity I can easily get, that is 114.13 meter per second. Okay. What exactly we have to calculate here is the angle at which the flow leaves the stage, right? blade angle at the inlet of the rotor, angle at which the flow enters relative to the moving blade, that is beta 1 we have to calculate. This is the question, first part. So now I know what is u, and to calculate this one I know what is ca also. So I can write either tan beta 1, that is going to be wt1 divided by ca, right? So see here, this is the Pythagorean triplet, so with which this is wt1, this is ct1, right? So u is equal to ct1 plus wt1. So wt1 I can easily calculate because I know what is alpha 1, I know what is ca or c1. So from here I can calculate what is ct1. So ct1, let us try to write in trigonometric relation, that is tan alpha 1 is nothing but ct1 divided by ca. So from here I can calculate ct1 because ct1 is nothing but ca times tan alpha 1. So if I use that one, I should be able to get ct1 as 37.082 meter per second. So now what is wt1? Wt1 is nothing but u minus ct1. So that is 200 minus 37, going to be 162.9792 meter per second. Okay, so now I know what is wt1, I know what is ca. So now I can use this idea, that is tan beta 1 is nothing but wt1 divided by ca. So if I use that one, beta 1 is going to be tan inverse of 162.92 divided by 114.13. So what do we get over here as beta 1 to be, yes, 54.98 or nearly equal to 55 degrees. So now look back to the given option. That option is not given. So the correct answer for this one is 54.98 degrees. Okay, that is not given. Since it is not given, so the next question kind of requires this information to proceed. That is why this is also given as grace mass, but this option we can actually calculate, right? So what they're given, if the mass flow rate of the air which is coming onto the stage is going to be 1 kg per second, then what is the power required by the compressor stage? So power required is nothing but mass flow rate of air times the work done in the compressor, that is u2 ct2 minus u1 ct1. Since it's an axial flow machine, I can write it to be m dot a times u times ct2 minus ct1, or I can also write, since axial flow velocity is also constant, so in this state, so I can take out ca. So from trigonometry I can write it to be tan alpha 1, sorry, tan alpha 2 minus tan alpha 1, or I can also write in terms of mass flow rate of air u ca times tan beta 1 minus tan beta 2. Anything I can actually write. And what else is given to you? In the problem, it is also given the flow turn angle beta 1 minus beta 2 is 27 degrees. Right? So that means beta 2 is nothing but beta 1 minus 27 degree, and beta 1 we calculated around 55. That is going to be 55 minus 27. So that is going to be something around 27 degree only, or 28 degrees. If I put the precise numbers, that goes 27.988 degrees. Okay, that is roughly around 28 degrees. Okay, beta 2. So now you can use the information what you got here. 1 kgs per second times u is 200 into axial flow velocity 114.13 times tan of beta 1, that is 54.98, minus tan beta 2, 27.988. So if you keep these numbers, you should be able to get power drawn as 20.4535. So 20.45 kilowatt. So that is roughly around 20.5 kilowatt. Right? So look back the given option. So option D has 20.5 kilowatt. Right? That's correct. So everybody clear, right? Yes. So that concludes our discussion on 2012 propulsion part from the GATE Aerospace paper. If you guys have any question, you guys can ask now. Okay, then we can wind up this session over here. Thank you. Thank you for your attendance.